rely on the color. So suppliers use different color codes, and then the label on the cap might differ. Okay, maybe you use the cap for one gas, and then you change it, you put it on another cylinder. The content might be different, but the cap is the same on it. So if you look at the cap to determine the content of the cylinder, it might cause harm. Careful procedures are necessary for handling the various compressed gases. The cylinders containing compressed gases, regulators and valves used to control gas flow, and the piping used in the gas during. So now there are careful procedures that are used regarding the filling of the cylinder, the regulator or the valve. So every cylinder must have a valve, and the valve must be on it always, unless the cylinder is not in use. Hello.
Hi.
And then there must be regulators that will regulate the flow of the gas, how it flows. There should be a regulator that will determine if it is flowing faster or slowly. Now, oxygen cylinders must have valves open up to all the way up to the high pressure. So when the valve of the oxygen gas and cylinder is open, it opens fully so that there will not be a leakage around it. When it opens fully, it gives it a firm grip that there will not be leakages around the cylinder. And the oxygen cylinders, full or empty, should not be stored in the same vicinity as flammable gases. Why do you think oxygen cylinders should not be stored around flammable gases? Hello?
Hi.
Yes. Why are we not supposed to store oxygen cylinders closer to flammable gases?
Because oxygen is combustible.
Is there? I didn't hear what you said.
Because basically oxygen support burning.
Okay, so oxygen supports burning, and oxygen is an oxidizer. It can easily cause fire when closer to flammable gases. Okay. We also see that proper storage of oxygen cylinders requires that a minimum of 20 feet be maintained between flammable gas cylinders and oxygen cylinders. So because oxygen, when stored closer to flammable gases, will cause fire, there is a need for us to leave at least 20 feet between each of them. So when you look at the image over here, we could see the flammable gas in red, and then the oxygen in green over here. So and then there is a 20 feet distance between them. And then grease and oily materials shall never be stored around oxygen gases. So these grease materials are also like flammable substances. They can easily, when they are stored around oxygen, they can cause fire as well. Now, things we are supposed to not to do. Never roll a cylinder to move it. Why are we supposed? Why are we not supposed to roll a cylinder? Yeah, Peter. Peter. Is Peter here?
Hello, sir.
Yes. Why are we not supposed to roll cylinders to move them?
Um, Due to the content inside, because the gases, the molecules, when you roll them, there will be collision of the molecules, so it
When
can
when you
easily explode.
okay, so when you roll the cylinder, it easily reacts and then it causes fire. And then
Yes.
we are not again we are not supposed to carry a cylinder by the valve. When you hold the cylinder by the valve and it removes, the gas tends to come out of the cylinder. And then in that case, when there is a source of fire, it can easily explode. Never leave a cylinder, an open cylinder unattended to. When the cylinder is open, you should never leave it unattended because when there is a source of fire or ignition, it is likely it will cause fire and cause explosion. Never leave a cylinder unsecured. So when you look at this image, you see the first one, the two which has the chain, it is secured. And then the second one, the three without any chain is unsecured. So you should never leave a cylinder this way, unsecured like this, because it can fall at any time and then it can cause fire because it is compressed. When it falls and then the potential energy is released, it can easily make the gas cylinder act as a bomb and then explode. Okay. Never grease oil, never grease or oil the regulator, valve or fitting of the oxygen cylinder. I've said this earlier. Why did I say this? Why are we not supposed to oil or grease the regulator?
Because they are flammable.
Because they are
Flammable.
okay, sure. And then never refill a cylinder. When the cylinders that are used at the lab, they are designed for specific um, chemicals. So when you refill and you fill with a different gas, there is likely a reaction will occur in the cylinder. So we are not advised to refill a cylinder. And I never use flame to locate gas leak. Why are we not doing that? Why are we not using flame to locate gas leak? Four, yeah, four. After four.
Sir,
Yes, why are we not supposed to use flame to locate gas leak?
it can cause burning or
Okay,
fire explosion.
okay. So when you use the flame to locate the fire and the leakage of gases, and then the gas is a flammable one, it will easily catch fire. So we are not supposed to use flame in locating gas leak. Never attempt to mix gases in a cylinder. This one itself is like when you mix gases in a cylinder, the gases react. And if the reaction gets becomes too much, the gas will explode, which will cause fire burning or explosion. Now let's look at how to store compressed gases. One, we have to properly secure the gas at all times. When I talk about securing the gas, we are looking at using belts, straps, or chains to hold the cylinders tightly. Look at the first image that the person has the cylinder with chains on them. And then we should keep the valve on unless the cylinder is being used. Look at the second image. We have the valve here. It should always be on unless we are using the gas cylinder. Now, store in a well ventilated area. The place where we store the gas should be well ventilated, because if it is not ventilated and then there is this the gases are released, they there will be a reaction between different gases, which can cause explosion, or even it can cause asphyxiation as well. Now we should keep the gas away from heat or ignition. Different gases have their flash point. So when there is let's say a gas has a particular temperature, or so if there is heat at the place where the gas is stored, it is easily that gas will cause fire. Or when it is near a source of fire, it can easily explode. And then we should keep away from electrical circuits, because some gases easily start fire when closer to source of electricity. And then we have to segregate oxygen cylinders. Like we said earlier, we should store oxygen cylinders separately. That is how we say we maintain a 20 feet distance between oxygen cylinders and flammable cylinders. Store flammable cylinders away from oxygen. Segregate full and empty cylinders. So we need to separate empty cylinders from the full ones. We should label the empty cylinders as empty and then label the full cylinders as full. Now here is a proper storage method. Look at this, the first image, and both the first and the second one. This is an example of a proper storage. Yes, this also. So here, excess cylinders should be stored in an approved storage area outside the lab. So these are gas cylinders that are not going to be used. So they are being kept outside the lab for safety. Now, things to remember. We must always wear eye protection when working with compressed gases. Only use regulators that have both high and low pressure gauge. Never refill a cylinder or use a cylinder for storing any material. We should know that the greatest hazard to a user of compressed gas is asphyxiation. Remember, except for oxygen, all gases are asphyxiants. So earlier I said, let's look at our last point. They said all gases except oxygen and air are asphyxiants. So how do these gases cause asphyxiation? How do these gases cause asphyxiation? Hello, we've said this already. How do these gases cause asphyxiation? Atu, are you there? Hello? Can you hear me?
Yes, sir.
Sir, we can hear you.
So I know what's talking.
So me, I just joined, so me, I don't know the answer. When
Atu. Okay, so asphyxiation is caused when the gas is in high concentration. So all these gas, they may not be harmful, but when they are in high concentration, they can cause asphyxiation. Okay. Now we are going to look at the sink. When you look at the sink at the laboratory and the sink at the house, what difference can you make from it? What can you deduce from the two?
I said the one at the lab is deeper than the one in the kitchen.
Is that the one at the lab is
It's deeper.
deeper? Okay.
Yes, in terms of depth.
In terms of okay, any other? Please, I'm listening. This is an image I have presented to you. So look at this, and we've all seen um, things at the kitchen before. So let's look at this image and the things in our kitchen. What are the difference? Or if you've been to the laboratory before, so you can see the difference between the lab sink and then the one at the kitchen.
Hello, sir.
Yeah, so
Yeah, please. The lab sink appears more rectangular than the kitchen one, and it's longer
okay,
in terms of length than the kitchen one.
okay. Now, all that you said is okay. And then the main difference has to do with the material. Because we will be washing acid, alkalis, solvents, salts, these sink at the lab should be made from materials that are highly resistant to these substances. So mostly you see the difference there. Those um, lab sinks are made from different materials as to the ones that are in our kitchen. Most of the labs, the ones that are in our kitchens are this aluminum metal, this soft metal. Now, we say that the lab should have a sink with drains for washing and disposal of liquids. So when we work with liquids, the weights are disposed through the sink. We wash it and then we rinse everything through the sink. Okay, so let's look at the emergency shower. or emergency eye wash. Has anyone seen something like this at the lab before?
No, please.
Okay. So this is mainly used when there is a chemical flash, maybe to your whole body or your eye. So when you are working at the laboratory, you should always know the location of the emergency shower. You should always know the location of the emergency shower and eye wash. You have to become familiar with operation, how to operate it. In case of accident, let's say you are working in the lab and there is a chemical spill there, then some enters your eyes or affect any part of your body. You wash the parts affected in a minimum of 20 minutes with running water. So the first image, you could see the person is washing the hair. So this is the running water. You stand under the shower and you wash the affected part in a minimum of 20 minutes. And then you remove all contaminated clothes. Let's say that the spill was on your clothes. After washing, you remove it and then you seek medical assistance. So this is like we say this is emergency. So it's like a first aid, something to keep you safe before you get further treatment. And then you report the incident. So what is the last step when we were talking about the electric shock? Hello. Last week when we were talking about electric shock, what was the last step? Hello.
Hello, sir.
Yes. Last week we were all here. What was the last step?
The last step is to use a stick to touch the affected person.
The last step we talked about.
The person must be taken to the hospital.
Christopher, we can't hear you well.
The person must be taken to the qualified medical officer or hospital.
Yes, but that is not the last step.
Hey.
You give the person water to drink.
Yes, you give the person water, but it's not the last step.
You must remove everything that tightens the person. Every dress.
Yes, but still, the last step is also here. It is general for all lab accidents. So
Report incident.
yes, so we always report the incident. You always report the incident so that you take note of it and then we improve upon it. Okay, so let's look at laboratory ventilation system. What is ventilation? What do we mean by ventilation?
The movement of air in and out of a room.
Okay, the movement of air in and out of the room. So since we are working in an environment where we use chemicals that can easily um chemicals that are volatile, they easily release vapor. There is a need for us to ventilate our room. If not that, we'll be working in a toxic environment. So we say why ventilation? Because because of worker safety. We need to keep the worker safe. We need to give the worker an environment that will not cause him or her to fall sick. Okay, and then ventilation because of space conditioning. When we say space conditioning, it is the control and the maintenance of indoor environment conditions. So making the laboratory environment a safe one. That is why we look at space conditioning, the laboratory indoor environment. We are making it safe for work. That's what we call the space conditioning. And then we look at optimizing. What is optimizing? What is optimizing? Hello. So when we say optimizing means making something as effective or efficient or even more functional. So optimizing over here means we are adjusting room, the airflow in the room. Okay, we are adjusting the airflow in the room so that we can achieve quality airflow. We can have a quality air in the laboratory. So we say the air change rate. We have to adjust the air change rate because we have to make sure there is a proper air circulation, there is proper air dilution. That is what we mean by optimizing. We are adjusting the laboratory air in such a way that we will have a quality air flow at the lab. Now, when we are dealing with hazardous chemicals, okay, one of the possible things we can do is to maintain a well-ventilated environment. No. Laboratory ventilation is the single most important factor that is used to protect people from airborne hazards. Chemicals come with so many airborne hazards. So most people suffer from lung diseases because they are working with chemicals and it's under a place that is not well ventilated. So there is a need to provide a well ventilated environment for our workers. Now, ventilation system can be separated into two. You can have the room ventilation, and then the local ventilation. Let's look at this. The dilution ventilation is also the same as the room ventilation or general room ventilation. And can you see from the image? Can we all read from here?
Yes, sir.
Is it visible?
No, sir, it's not. We can't read.
Okay, let me see if I can adjust. Is it okay? Is it okay now?
Yes, sir.
Okay. So the dilute ventilation, it dilutes contaminants to an acceptable level. I hope we understand dilute. Hello. When we say it dilutes contaminants to an acceptable level, what does it mean?
It makes it less concentrated.
It makes it less concentrated. So we let's say the the operator or the source of the contamination, it has already spread to the whole room. Okay, so in this case, we need to release air that will mix with the contaminant, and then it will per time it will just clear all the contaminated air. It will mix with the contaminant, and time as time goes on, it will just clear the contaminants from the atmosphere. So it comprises of fan sets in walls. So you can see some over here, fan sets in walls. It's it's also cheap and simple. It's limited application as a control strategy. Now when you look at the local exhaust ventilation, it captures contaminants closer to the point. So at this point, this one, when the the air is released, at the point where the air was released, the local exhaust captures the contaminant at that point. So here it's not spread, it doesn't spread, it just captures it even before it starts to spread. So it comprises of food, so duct work, and then filter. We will talk about them one after the other. Okay, so the dilution ventilation, it changes the whole workplace air over a given period of time. So when the contaminant has been spread, and then the dilution ventilation, it releases air that will just occupy the whole room, and then it will displace the contaminated air over a given period of time. Now, it is limited to circumstances where exposure limit is high. So when the the, the contaminant has already been dispersed, and then it is highly concentrated in the room, that is where we use this approach. And then we say it is used when the particles or the air has already been spread. So it is used for chemicals or substances in which the spreading limit is low. The chemical spreads slowly, or it is emitted gradually into the air. And then it is used for liquids that release vapor slowly. Liquids that release vapor slowly, one after the other, it releases slowly. So in that case, when the the dilution is taking place, it also clears it with in a given time. So let's look at the general room ventilation. Laboratory room ventilation consists of an air supply and air exhaust system. So here, there's an air supply system, a place where the air passes through to the lab, and a place where the air leaves the lab. The supply system introduces clean air into the lab, into the room, and the exhaust removes air from the lab. So most of these labs that have supply and exhaust system, mostly they can be used when the doors uh, and windows are closed. So in that case, there's already a system that allows air in and air out. So we can use the lab even when the doors and windows are closed. So let's look at general room ventilation. So I said the general room ventilation is also the same as the dilution ventilation. Okay, so we say based on the volume of space in the lab and the volume of air exhausted, an exchange rate can be determined. So we can derive an exchange rate based on the space of the lab, how big the lab is, the volume of the lab, and then the amount of air that is exhausted, the amount of air that is removed from the lab. We can generate an exchange rate. Okay, this exchange rate is expressed as air exchange per hour because we said the air for a given time interval, the air is the air supply displaces the air that is the contaminant. So per the time that it takes to clear the contaminant, we can express that in an hourly basis. Okay, air exchange rate. The higher the exchange rate, the faster the airborne contaminants are exhausted. So how fast um, we can exchange the air, how fast we can get air supply, okay, how fast we can get that determines how the rate at which airborne contaminants can be taken out of the lab. Air exchange rate for laboratories range from 8 to 12 per hour. So per every hour, we can change the air for like 8 to 12. Okay. Now, let's look at the negative pressure. What is negative pressure? What is negative pressure? So when we talk about negative pressure, yes, okay, wisdom.
Yeah, so the negative pressure is when the air content in the room is lesser than the one outside. That is, the air leaving the room is like higher than the air that is coming into. So because the air leaving the room is higher, the concentration of air in the room is lower than the air outside.
Okay. So the negative pressure means that the air pressure inside the lab is lower than the one outside the lab. So here we say laboratories should exhaust air at a higher rate than supply. So the air that is coming in should be we should be able to take more contaminated air out than the fresh air that will be coming in. Okay. Now negative pressure prevents air from migrating from the lab into adjacent areas. So because there is a negative pressure, there will not be, the air will not be able to move to different, like the corridors or adjacent any area of the lab, except through the exhaust outside the lab to out of the lab. But then it will not be able to migrate to other corridors of the lab. Now, most laboratory ventilation systems are designed to function with doors and windows closed. So in this case, when the doors and windows are closed, the only point that the air can leave or air can be exhausted is through the exhaust. So there is no need for us to open windows. When the windows are open, in that case, the air can leave to other corridors of the lab. Now, let's look at the local exhaust.
Hello, sir.
Yes, hello.
With the negative pressure.
Okay.
Well, once the pressure inside the lab is low, I think that that will allow more air to enter to displace the air inside, since the pressure outside is greater than the pressure inside, just as we have in breathing in and breathing out.
Can you come again?
What I'm saying is that when you said the negative pressure, we don't even need to open the windows, because
Okay.
if you open the windows, the gas, which is the contaminant, will spread to the other part of the building, which is the corridor or the other part. And I'm saying that if we open the window, won't we allow other gases or the air outside the lab to enter the room or the lab, since the pressure outside is greater than the pressure inside, just as we have in respiration, yes, or breathing.
Yes, so in that case, air flow into the lab when the doors are open.
Mm-hmm.
Okay. But then the air does not flow to the corridor or adjacent room, because there is a low pressure in the lab than the surrounding, than the pressure outside the lab. So we need to keep the pressure in the lab lower than the pressure outside.
So that the air outside will displace the air inside. Oh,
Yes, yes.
okay. Thank you.
Can we continue?
Yes, sir.
Okay. So we are coming to look at the local exhaust ventilation. So the local exhaust ventilation has a hood or an exhaust inlet. Okay. And then these are some of the parts that we have. We have the receptor hood. So the receptor hood, it directs the contaminants into a large hood. Okay. So the receptor hood directs the contaminant into a large hood or a closure using the fan assisted draft. Here, airflow pulls the contaminants from the lab towards the hood. So the air here, there is a receptor, okay, and then it pulls the contaminant, and then it directs it into a large hood by the use of the fan assisted draft. And then there is a capture hood. So the contaminant is captured by air close to the point of generation. So where the contaminant is generated, where it is coming from, the capture hood captures it at that point. It captures the contaminant at that point. And then it does that in low pressure, large volume. So it maintains a low pressure, and then it it captures them at a large volume. Please, are we getting it? Hello.
Hi, sir.
So here, the contaminant does not disperse. Okay, it just captures it. Unlike the local the general room ventilation, where the contaminant disperses and then the air is the air displaces it. Here, it does not disperse. It just captures it right at the generation, the point where the contamination is occurred, where it is generated from. This one captures it at that point. And then we have a ducting. This is the ducting. Okay, it is a straight, gentle bends and angle joints. Then so the ducting transports the contaminant air safely from the hood. So when the air is being trapped, this ducting transports the contaminant. When the contaminant is trapped at the source, this ducting transports it. And then we have a filter. The filter also removes the contaminant before releasing it out. Okay, so the filter also removes the contaminant before releasing it out. It uses cyclone. This cyclone uses centrifugal force to separate the contaminant from the air. It also uses washers and electrostatic forces. Now, the local exhaust ventilation system captures or contains contaminants at high source. So why do you think it has the contaminant at high source? Hello. Hello.
Hi.
Hi.
Yes. Why do you think it has the contaminant at high source? I can't hear you. No, nobody is speaking.
Hello, sir.
Yes.
The high here means, is it the height? I don't really get the high source.
So when I say the high means like there's a higher concentration.
Okay.
So because the local exhaust ventilation, it captures contaminants at the source where it is starting from. Here it does not spread, it does not disperse before the ventilation occurs. So it captures the contaminant at the source where it is being generated. So it gets it at a high concentration.
Okay.
Okay, so these contaminants are typically exhausted through a roof duct. So these are the roof ducts, the ducting that I showed earlier.
Yeah.
Okay, so example of this local exhaust ventilation ventilation is the flexible reaching hood. The flexible reaching hood. Let me show you the flexible thing. Oh my, coming. Please, I'm coming here.
Okay.
But where are the ladies? Hello.
Hi.
Where are the remaining? It's like today we have only 4.
I don't know.
Or they've gone to church already.
I'm sure.
Okay. Let's see. So this is the flexible reaching hood. So you see how it is. It is very flexible. Now, the flexible reaching hood, it captures less toxic substances located next to the intake. You see, you cannot pick it. You see where it has been installed. It has
Yes.
limited. You cannot put take it to different places. So it only captures toxic substances that is around it. So the main benefit is that it can be removed or relocated. So you can remove it from where it is and then fix it at another point. But for where it is, it can only capture contaminants that is closer to it. So here we say contaminants that are 60 centimeters around the intake point.
Okay.
Yes. So that is the biggest drawback of it.
Yeah.
Now, let's look at another type of local exhaust ventilation. That is the glove box. Now, the glove box isolates and exhausts highly toxic materials. So you see, it's a box, and then it has a place where you put the chemical inside or the toxic substance inside, and then we use an inbuilt glove. We put our hand in it, and then we use to operate the substance. So it isolates the substance, and then it exhausts the toxic that will come out of it.
Okay.
Are we getting it?
Yes, sir.
Okay. So it isolates item within the box from the normal air in the environment, in the lab. So it isolates or it takes because we put the substance in the box, it isolates it and then it makes the air around us okay for us so that the substance will not contaminate our air.
Okay.
Now, the box maintains positive pressure to prevent migration of air into the box. So the box is such a way that there cannot be air in and out unless through the exhaust.
Okay.
So here is the exhaust, the glove box. Now we say the biggest drawback is that the work area is small and then manipulation of material can be difficult. So you see how it is.
Yes, sir.
When you put your hand in the working area, it's small. And then it makes sometimes working with substances inside becomes very difficult. Okay, so we look at another example of local exhaust ventilation. That is the chemical fuel hood. I hope this one we've all seen that before. Have we seen this before?
No, no, sir.
Hey, so you've not seen them before.
Yes, sir. I've not seen something.
Wisdom, have you seen some before? Okay, so with the chemical fuel hoods, all chemical fuel hoods are equipped with a motor. Okay, and then the function of the motor is to power the exhaust fan. You see, it works with an exhaust fan. The exhaust fan will cool the contaminated air. So there should be a motor that will power the exhaust fan to cool air through the hood. And then it has an exhaust fan that draws contaminated air from the hood. And then we have a duct work with a roof exhaust duct. So chemical fumes safely it channels the fume safely out of the building. So this fume, it has a ductile that is channeled to the roof of the building. So that is where the chemical fume that is being used in the fume hood passes to be exhausted out of the building. And then it has a sliding sash. The sliding sash acts as a physical barrier between the person that is using the chemical fume hood and then the chemical that is being used. Are we getting it?
Yes, sir.
Yes. So the sliding sash serves as the physical barrier between the person that is using the chemical and then the chemical fume hood. Okay. Again, we have an airflow alarm. We have an airflow alarm, and the alarm notifies the user if the air is not flowing properly. If the air that is coming from the fan is not flowing properly, the airflow alarm notifies the user so that you can check what is wrong with the fume hood. And then it has a motion source. It detects if the hood is not in use, and then it automatically reduces the the speed of the fan. So the motion sensor detects it detects if the fume hood is not being used. So if the fume hood is not being used, the motion sensor detects it so that it will automatically lower the speed of the fan. Please, are we getting it? Hello.
Yes, sir.
Are we getting it? Any question?
No, sir, from my side.
Okay. Okay, so we continue. It also has a spark height sensor. And the height sensor monitors the position of the sliding sash. So it monitors the position of the sliding sash. We've spoken about the sliding sash, right? And then we look at the sash stop. The sash stop physically limits how far the such can be opened. Okay. So we say the fume hood needs to be available for use and functioning efficiently at all times. So that the all the time the fume hood has to be available so that we can use it when we are working with volatile chemicals. Now, volatile chemicals need to be used in the fume hood when feasible. So what are volatile chemicals?
Hello.
Yes.
Yeah, yeah, chemical that's easily evaporate.
Okay. So when we are using chemicals that easily evaporate, we need to use the chemical fume hood because when it evaporates, it releases steam into the atmosphere, and that can be very toxic depending on the kind of chemical that is being used. So we need to use the chemical fume hood when we are operating with volatile chemicals. Okay. So the lab fume hood is not a place where we store chemical equipment. So when we are done using the particular chemicals, we are not supposed to keep it in the fume hood. We don't store chemicals there. And then the fume hood is not designed to collect particles. Okay. These are some of the things we have to know before and during the use of a laboratory fume hood. So one, we have to check the hood certification sticker on the front of the hood to ensure that the airflow is between 80 and 120 when tested. Hello.
I say,
Why is every,
Hi.
why is everyone quiet? Why is everyone quiet? Okay. So check visual alarms to ensure that the hood is functioning properly. And then you hold a tissue at the face of the hood air to ensure air is flowing in the hood when the fume hood is turned on. Okay. So when you put a tissue in front of the fume hood and then you on it, you feel the air blowing the tissue. In that case, you know that the fume hood is working perfectly. And then during this, when you do all this, we do all this to ensure that the fume hood is functioning properly. Please, I'm coming. Hold on. Okay. And then you check the baffle to be sure slots are open.
hello, sir.
Yeah, hello.
Yes, sir. So when you go to the other slide, the
Which one?
the the slide before this one, yeah. So we have. You said the air should flow in between 80 and 180, 120 FPM. The FPM is
The FEM is the air speed.
uh
Air speed.
Okay.
Yes, that is the airflow speed, the air speed.
All right. Thank
Please,
you.
are we okay? It is used to measure how fast the air is moving.
Okay.
Okay. So the FPM means feet per minute.
Oh, okay.
Yes, feet per minute. It's a velocity unit that is used to measure how fast air moves.
Oh, okay.
Okay. So you ensure all chemicals and equipment are at least 6 inches behind the sash. And then you elevate equipment with blocks or racks to maintain efficient airflow. So you keep the sash as low as possible. You close it when you are not using it as well. And then you decrease the turbulence by opening or closing sash slowly. We avoid swift movement inside or outside the hood. Perchloride acid must be used in a downwash hood, which is designed for such use. Hydrochloric acid needs to be used in an acid hood designed for such purpose. Verify the hood is functioning properly before you use it.
Oh, okay.
Okay, so we move to another aspect, which is chemical grade and purity. Now let's do the discussion here. What is chemical grade?
For me, the chemical grade means the quality of the chemical.
The quality of the chemical.
Yes, please.
Okay, another, any other? Atapor.
So I would say is the purity of the chemical.
The what?
The purity.
Okay, Yakubu.
Yes, it refers to the purity of the chemical.
The purity of the chemical.
Yes, please.
Okay. So do you have something to add? Hello.
Yes, sir.
Do you have something to add?
No, sir.
Okay. So when we look at chemical grade is the classification of chemicals based on their purity and then their intended use. So the following are some of the chemical grades that we have. Okay. We have the spectroscopic grade, and the spectroscopic grade is high purity chemicals specifically prepared to be used for spectroscopic analysis. Now, the over here, the purity determined by optical absorption at a particular wavelength, usually around 99%. So when you take a spectroscopic grade, the purity of those chemicals are around 99%. Yeah, their purity is around 99. And then they are used for infrared, um, they are used for infrared radiation like visual radiation, and then ultraviolet um, spectrometry. And then we look at chromatographic grade. And this one too, they are mainly used for chromatography. They are used for chromatographic analysis. The- And then they have a minimum purity of 99%. Okay, the impurity that will come from a chromatographic grade it should not be over 0.2%. So mostly all the chemicals under this part are 99.8, 99.7. The purity that will come at this point should not be more than 0.2. And then we have reagent grade or reagent analyzed. It is certified to have impurities below specific levels set by the Committee on Analytical Reagents of the American Chemical Society. So they, this ACS, they set a specific level that this particular reagent should have a purity. So they set a purity that chemicals that are classified under reagent grade should have. And then bottles are identified by batch number. So every chemical that is under this grade, the bottle has a batch number. And that batch number is used to identify them. Also, a minimum standard for any chemical analysis work. And then we can have commercial or technical grade. These chemicals typically have purity of 85 to 90%. So here, what will be the impurities of them? What percentage of impurity will be in commercial or technical grade?
15 or 10.
Okay, so 15 or 10. Okay. So these chemicals are rarely used in the laboratory. They are mostly not used in the lab. And then we have practical grade. So they are small steps above technical grade. They often contain intermediate compounds as part of the preparation process. Now we have United States pharmacopoeia, which is the USP grade. They are suitable for drug use. Okay, and then they are generally acceptable for chemistry lab work. We have the chemically pure grade. They are almost as pure as reagent grade. But their application determines whether purity is adequate for the purpose. So per what they are going to be used for, this particular one, per what they are going to be used for, will determine if their purity is adequate or it's not adequate. And then we have electronic or semiconductor grade. They are specified to contain less than set level of specific impurity. The examples are sodium, potassium, and their common subdivisions are low sodium. So these electronic and semiconductors, their subdivisions are low sodium grade. And then they have the low sodium. First one is low sodium MOS grade, and then low sodium CMOS grade. And then we have the primary standard grade, at least a purity of 99.95%. Is there a question? Yes, Arthur.
Yeah, sir. The MOS, what does it stand for?
Can you come
Please,
again?
I want to know what the MOS and the CMOS stand for. That's the low sodium CMOS grade.
I'm coming. Yeah, hello.
Hello, sir.
You were saying,
I
you
said
said
with
that.
regard to the low sodium MOS grade and the low sodium CMOS grade, I want to know what the CMOS and MOS stand for.
So the MOS means the margin of safety. Can you hear me?
Again for me.
Hello.
Hello.
Yes. So the MOS means margin of safety.
Margin of
Margin of safety.
okay.
Nothing said margin of what?
Margin of safety. Safety.
The last word. Margin of safety.
Safety. As in
Safety. Oh,
SAFETY. Yes.
okay, sir. Thank you, sir. Okay, sir.
And the CMO means complementary margin of safety.
Okay, sir.
And please, is that okay?
Yeah.
Okay. So we say they can serve as a reference standard in analytical procedures. And then we have ultra high purity grade. They are usually solid that have been successively refined, and they are expressed as a number of 9. Example, 5 into 9s. So here, when you see something like 5 into 9s, it means the 9 together with the dot should be 5. Is that okay?
Sir, please come again.
Please come again.
Okay. So let's look at the example over here. Can you see where the mouse is?
Yes, please.
Can you see we have 5 into 9s, right? Hello.
Yes, sir.
Can we see this?
Yes, please.
Yes, sir.
So let's count the number of 9s we have here.
Oh, okay.
How many do we have?
5.
That's 99.999.
Okay, so when we have 6 into 9s, then how many 9s are we going to get?
6.
6 9. Okay, so we said they are the highest purity of any material. So here we are getting the impurity to be about 0.1%. Is that okay?
Yes, sir.
Okay. So we are going to look at National Fire Protection Association. But before we do that, let's take about 10 minutes break. Let me take some water, okay? Please, is that okay?
Yes, please.
Yes, sir.
Uh,
We are also preparing for crossover.
and we are all preparing. I'm a man of God, so I'm also preparing. Yes, so yeah, so for that matter, we might close early so that we prepare and go to church. And then let's use this opportunity to talk about the past questions. Are we here?
Yes, sir.
Yes, sir.
So the where I'm supposed to get it, they due to the break, so I'm not getting it. But then when they resume, I think you resume on the 5th. So when we resume, I'll try and then I'll get it for you.
Oh, okay, sir.
Okay, sir.
Okay, sir.
Yes, and it's going to be a hard copy, so maybe I'll take pictures of them and then make it in a PDF form and share with you. I hope that will be okay.
Yes,
Yeah.
please.
Okay, so let's have some break and then get back.
So please, when are we coming back?
Uh, from the break, this break.
Yes, please.
Oh, I think it's 10 minutes. So let's say 6:20 or 6:20. 6:20.
Okay, fine.
Yeah, hello. Hello.
Hi, hi.
Okay, so we are back.
Yes, sir.
Okay. So before we continue, let's look at this question. Let's discuss them. This is how we are going to do it. Um, let's all find solutions to this question. Let's do it independently and then we share the answer later. So I'm giving you some time to find solutions to this question. Is that okay? Hello. Hello.
Hi.
And please, can you hear me?
Yes, sir.
Okay, so let's all find solutions to this question. So I'm giving you some time and then you find solutions when the time is up. Everybody presents his or her answers on these questions. And please, did you get me?
Yes, sir.
Okay, so let's start. Please, your time has started, though, so start finding solutions. Wherever you find answers, you come and explain to us.
No, I'm done.
Christopher, are you done?
Yes, sir.
What about the rest? Are you done? Four. Four, are you done? Hello, Paul. Paul, we can't hear you. Are you done? Apple, are you done? Apple, I cannot hear you guys. So, are you done?
Yes, sir.
Okay, Christopher, I want to hear from the remaining. I want to know if they are all done. Apple,
Okay, okay, sir.
Yes, sir, sir, we are done.
okay. So let's look at the first question. We are saying why acids are added to water and not the reverse.
Okay. So what I have here
Yeah.
is one is the reaction control.
Peter, you said?
Reaction control. Yeah, please, I said due to reaction
Due to
control.
reaction control.
Yes, sir.
Okay, Paul.
Hello, sir.
Yes.
Please, I want to try.
Okay, we are listening.
Yeah, please, because of the corrosive nature of acid,
Okay.
when you add acid, it's right better to add acid to water than water to acid, because when you add the water to acid, it causes what? Splashes. It causes splashes which can cause burn to the skin.
Okay, Paul, your hand was up. Paul, check your microphone. We cannot hear you. I think you are talking, but we can't hear you. So Christopher, let's hear you.
Sir, please, acid
Hello.
is added to. Hello.
Okay, Paul,
Hello.
wait. Paul, wait. Christopher is talking. Okay, Christopher, let me hear
Acid,
you.
acid is added to water to reduce explosion, another heat highly heat generated. So if water is added to concentrated acid, the heat generated can cause the mixture to splatter or even boil violently.
Okay. After 4, let's hear you now.
So okay. When water is added to acid, there is exothermic reaction that is going to take place, and this reaction can cause serious explosion of the corrosive substances, which is the acid. So it is rather good to add acid to water and not water to acid.
Okay, sure. They are all correct. So when you add acid to water, the water absorbs the heat safely. But when you add hello, is someone saying that? But when you add water to acid, it causes a splash which can cause explosion. So it is advisable to add acid to water instead of adding water to acid. Now let's look at the second question. Why is nitric acid stored separately from all other acids?
Hello, sir.
Yes.
Hello.
Yes, I can hear you.
As I said, nitric acid is highly reactive and corrosive substance that can react with many other substances, including other acid. It is often stored separately from other acid because it can react with them to produce toxic gases.
Okay. Yeah, Apple. Emmanuel Asante. Okay, Paul.
So, as you said, nitric acid can cause burns easily. So it is advisable to separate it from other chemicals, especially due to its strong oxidizing nature.
Okay. So nitric acid is a strong oxidizing agent, and then it reacts violently with organic materials. That is the reducing agent. So when it is not stored separately and it is stored with other reducing agents, it easily causes a reaction between them, which can cause an explosion. That's why we store nitric acid separately. And now, why most alkalis are stored in a plastic bottle? Why? Wisdom. Wisdom. Is wisdom here? Okay, so let's continue. Anyone?
Hello, sir.
Yes, I said.
Okay, Yakubu.
Yes, sir. So it is stored in plastic bottle because when it is stored in glass, it reacts with the glass and make the glass very weak, and it can break the glass.
Okay, Christopher.
That means most alkalis, such as sodium hydroxide, are highly corrosive and can react with glass, especially at high concentration. Glass containers can be damaged by alkaline, leading to contamination or leakage.
Okay, any other?
Hello, sir.
Yes,
Hello, sir.
Emmanuel. Yes.
So most plastic containers are not able to react to
You said hello.
acid.
Hello. Emmanuel.
So it's better to store them in plastic than.
Can you come
Hello,
again? We
sir.
didn't hear. Yes. Yes, I can hear you.
I said most plastic they are chemically resistant. So it's
Okay.
very for them to react. Yes, chemically.
Okay.
Sir, please, can you hear me?
Yes, I can hear you now. I think its network is failing. So most plastics are chemically resistant to alkalis. They don't react with alkalis. But when you store alkalis in glasses, the alkalis, they are the strong alkalis like potassium hydroxide and sodium hydroxide. They react with the glass, which makes the glass very weak, and they can even crack over time. So that is why it is not safe to store alkalis in glasses, but then we store them in plastic bottles. And then the last one, why is sodium hydroxide usually placed in
Sir, please come again. Sir, please come again with the third point.
so I'm
Why
saying
most
that
alkalis are stored?
alkalis react with glasses, okay? So they react with glasses and then they make them weak and then they can even break over time as they keep reacting with it, they break the glasses. Okay. So they react with the glasses and then they make them weak and then it breaks over time. So it's not advisable to store them in glasses. But with the bottles, most bottles are resistant to alkali. They don't react to alkali, so we can store them in the plastic bottles. Is it okay now? Okay, so why is sodium hydroxide usually placed in conical flasks instead of burette?
Hello, sir.
Yes, yes, I'm listening.
Sodium hydroxide is a strong base that can.
Why sodium hydroxide?
Hello.
Yeah,
Peter,
sir.
wait, let's listen to Christopher.
Okay.
Christopher, let me hear.
Sodium hydroxide is a strong base that can
Okay,
react with the glass of a burette, causing it to become damaged over time. This can lead to inaccurate measurement and potentially contaminate the solution.
okay, okay. Peter,
Yeah, to me, I guess it minimizes spillage.
it minimizes.
Spillage. That is the narrow neck of the flask reduces the likelihood of the spillage, or especially
Okay,
during whiling or pouring, and making handling safer.
okay. So when the sodium hydroxide absorbs carbon dioxide from air, okay. So when it is
Yeah.
being exposed for a long time, the concentration reduces. Okay. So when it reduces like that, it makes us get inaccurate results. Okay. because when it's exposed to air, the concentration that we are using, it reduces, so it makes us get inaccurate results. That is why mostly they are placed in the conical flask instead of putting them in a burette. Okay, so let's move on to the next, what we have left. Now we are going to look at the National Fire Protection Association. Now, when we say the National Fire Protection Association, they are it's a US based organization that develops standards and codes for fire safety and hazard communication. So they develop standards and codes that are used to that we use to protect ourselves from fire outbreaks, and then it is also used to communicate hazards of chemicals. Okay, so we say the National Fire Protection Association 704 provides a simple, easy to recognize and understand system of making of markings that provide information regarding the hazard of a material and the severity of these hazards as they relate to handling, fire prevention, exposure, and control. So when you look at their symbols, they have numbers in them, and these numbers tell you the the how extreme the hazard can be. Okay, so the code for standard system for the identification of hazards of materials for an emergency response. So they are also the codes that are used to identify hazards of particular materials so that we can respond to them early. So this is how the hazards are rated. So they are rated from 0 to 4. Okay. Hello.
Hi.
Okay. So they are rated from 0 to 4. And then 0 means there is none. And then 1 means it's slightly. When you see 2, it means the hazard is significant. And then 3 means it's severe. And 4 means it is extreme. Now, let's move on. So this is how the symbol is like. The National Fire Protection Diamond. The symbol is in the form of a diamond. That's why we say the National Fire Protection Association diamond. So it has these colors. It has the blue, the red, the yellow, and then the white. Now, the blue means health hazard. The red means fire hazard. The yellow means reactivity. And then the white means specific hazard. Okay, so when we look at the blue, the health hazard, the 0 means normal material. So this is how it is being rated. Okay, now let's look at an example like so. Okay, so let's look at this. An example of this. When we have something like this, we can say all means material with an oral lethal dose of 50, lethal dose of less than or equal to 5. Now, what is a lethal dose? What is a lethal dose?
Where is it?
Hello.
Hi.
Yes, what is lethal dose? Hello.
Hi.
Yes. What is lethal dose?
Letter do. How do you spell it?
Okay. So when we talk about lethal dose, what someone speaking?
No, sir.
Okay. So lethal dose is the amount of a substance that can cause death when it enters a body. So, and please, is that okay? The amount of a substance that can cause death when it enters the body. So when we were looking
Yes,
at
sir.
the rate, when we were looking at the rating, we said 4 is what? Extreme, right?
Yes, sir.
So here, the health hazard over here. This is blue. We are talking about blue. So blue is what? Health hazard. And then the four means the material has a lethal dose less than or equal to 5. So when it is 4, that means it is extreme. So when you take just small quantity of it, it can cause death. Please, is it okay?
Yes, sir.
Hello?
Hi.
Okay. And then 3. When we
Yes,
look
sir.
at
It's
the
okay.
third, when we look at the 3, we said material with lethal dose above 5, but less than 50. Okay. So let's say the symbol over here, the symbol over here, if we had the blue to be um 3, what does it mean? Can you all see the symbol?
Yes, sir.
Okay. So let's look at the 3. Over here we have 1, right?
Yes, please.
The
Yes.
blue, the blue.
Yeah, one.
Okay. So let's say we had 3. What or we have 2. What does it mean? Let's say the number in the blue was 2. What does it mean? Yeah, Paul, we can't hear you.
If it's true, I would say the material with an oral dose about 50, but less than 500
Okay.
milligram.
Okay. So it means the material has a lethal dose of about about 50, but less than 500 milligrams. So in that case, if you take above 50, it will cause what? It will cause death. And then 1 means the material has a lethal dose above 500, but less than 2,000. And then 0 means the substance has material dose above 2,000. In that case, it is highly the substance will cause death. It is less, like you have to take about 2,000 milligrams before it can cause death. So this is for blue. Now, and we say blue stands for health hazard. Let's move to yellow. So let's look at the yellow. Four means the material is capable of explosion at normal temperature and pressure. So when you are handling a substance like this and you see it has the yellow, we have, let's say, a symbol like this on a substance, and the number in the yellow is 4. It means that material is capable of explosion at normal temperature. And then we have 3. 3 means the material is capable of explosion, but requires a strong i- initiation source. Over here at the 4, when it gets closer to small initiation, it can cause explosion. But the 3, it means it requires a strong initiation source before it can cause fire. Okay. Now, 2 means the material undergoes violent chemical changes at elevated temperature or pressure. And then 1 means the material is normally stable but can become unstable at elevated temperature. And then 0 means that the material is normally stable. So when you look at the symbol, the number that will be placed there will tell you how you are supposed to handle the chemical, and then what you should know about that particular chemical. Now, the red means flammability. So when you see 4 at the over here, the symbol we have here says it is 0 flammability. So meaning this particular substance that has this label, the material which normally is a material which normally won't burn. It's a material which normally won't burn. And then the 4 is a material with a flash point below 20. What did we say a flash point is? Hello. And please, we talked about this in the first when we started this lesson today. We talked about flash point. What did we say flash point is? Please, I'm waiting for you. Isaac Amate. Isaac. Hello, Isaac. Isaac is not here. Ato. Ato. Okay, Paul.
Okay.
Yes, what did we
So
say
the
flash
person
point?
again.
What did we
What?
say a flash point is?
So I would say how harmful the material may be. That will be the flash point.
Flash point. Okay, Christopher.
Sir,
Yes, what is a flash point?
it refers to a point at which a substance bursts into flame.
Yes, we talked about this in the first. That was the first thing we spoke about. It said the flash point is the lowest temperature at which a substance can catch fire. Okay, so we say when we have 4, it means the material has a flash point below 22 degrees Celsius and a boiling point of 38. And then 3 means the material has a flash point below 22 and a boiling point greater than or equal to 38. When we have 2, it means the material has a flash point above 38, but not exceeding 93. And then 1 means the material has a flash point above 93 degrees Celsius, 93.3. And 0 means as normally the substance will not burn. Please, are we okay?
Yes, sir.
Okay. And then for white.
Yes, sir.
Okay. For the fight means special hazard. So at that place, mostly we don't have numbers over there. We have symbols like this. So when you see something like W, mostly W and it's being cancelled or W, it means water reactive. That means the substance is reactive to water. When you see OX, it means the substance is an oxidizer. When you see COR, it means the substance is corrosive. And then when you see this symbol, the symbol over here, it means that the substance will cause or emit radiation. Let's look at the chemical storage. So these are 4 storage methods. Okay, so we have the chemical storage code. So these are the codes that are used to store chemicals. So basically, when you see a chemical labeled with orange, it means they are inorganic acids. And then when you see yellow, it means we have an organic acid. A dark green means that is a base. So mostly they are being labeled on their container or where the shelf in which they are stored. So blue means it's an oxidizing or special handling inorganic acid. Then light green is also means it's an oxidizer. Then purple means they are toxic. Red means flammable. And then white means general chemical. Okay. So these are the general rules for chemical storage. So we need to label all chemical containers appropriately. All chemical containers, we need to label them. The label will tell us the exact chemical that is in and then the quantity that is in. So we have to label all chemical containers so that when we are picking a chemical, we know this is what we are taking. and then place the user's name and the date received on all purchased materials in order to facilitate inventory. We provide a definite storage place for each chemical and return the chemical to that location after use. So when we have a storage place for every chemical, and then you have to return it to exact place after using it. When you pick the chemical, wherever you picked it from, you have to return it to that same place after using. And then avoid storing chemicals on bench tops. You you have to get a cabinet where you you store your chemicals. You don't have to leave the chemicals on the bench where experiments are being conducted, and that is where you are saving your chemicals. No, we don't do that. So you only keep chemicals that you are using currently on the bench. Aside those chemicals, all other chemicals need to be stored in their respective places. And then let's the organization of and chemical segregation. Organize chemicals first by compatibility. What does compatibility mean?
So I think it substitutes.
Is that
I said compatibility if the chemical can be substituted by other chemicals.
okay? So compatibility means you can add the chemical to another or keep it closer to another chemical without causing any hazard. Okay. So over here we are looking at we store chemicals in terms of compatibility, not alphabetic session. So if we are storing the chemicals alphabetically, we have to look at chemicals that are compatible, chemicals that when you bring them closer, it will not cause any accident or hazard. Then that ones we can store them alphabetically. But then we store chemicals compact by compatibility, not alphabetically. We look at this chemical can be saved around this one. So we store them close. Okay. Store alphabetically within compatible groups. So when we look at the chemicals that are compatible, then we store them alphabetically. Those chemicals that we can add, those that are compatible, then we label them alphabetically and then we store them. So you store acids in a dedicated acid cabinet. So we've already talked about why nitric acid should be stored separately. So we have to get a cabinet dedicated for storing acid. Okay, and then nitric acid alone should be stored separately. And then store highly toxic chemicals in a dedicated lockable cabinet that has. Okay.
I have a question concerning the nitric acid. Yeah, is it that only one in a bottle should stored at a separate place, or all the nitric acids? Let's say assume we have about 3 or 4 or 5 bottles, they should be stored at one
Yes,
place.
they should be stored at one place.
Oh, okay.
Yes.
Thank you, sir.
Okay. So you store highly toxic chemicals in their dedicated cabinet, a cabinet that you can lock, that has been labeled very, very visibly. So you have a cabinet that is labeled toxic chemicals, and then you store those chemicals over there. And then store volatile chemicals in a ventilated cabinet. Why do we need to store volatile chemicals in a ventilated cabinet?
Hello.
Yes.
Hello, sir.
Yes, Christopher.
Yeah, this is because when the room become hot, since the volatile could evaporate at low temperature, all of them will evaporate.
Okay, so
Will
because
be
they,
evaporated.
yes, because they easily evaporate. So if the room is not ventilated enough to replace those evaporated air, they become very, very toxic, and they can cause asphyxiation, or they can even cause explosion as well. So we store water sensitive.
So
We
please,
store water.
on
Okay.
I said on the side of the why volatile chemical volatile chemicals are stored in ventilated cabinets. I want you
Okay.
to go over that one for me.
So you see, volatile chemicals, they easily evaporate. Okay. So when they evaporate, and then the room is not ventilated enough, the chemicals stay in the room. Okay. So when they stay in the room, they can react with other chemicals that are there, or they can even cause asphyxiation. Okay. So we store water sensitive chemicals in a water tight cabinet and a cool and dry places. Some chemicals, they easily react with water. So in that case, we store them at a dry place so that they don't get access to moisture or water. So we store flammables in approved flammable liquid storage cabinet. So we need a cabinet that we store flammables in because they easily catch fire. Flammable substances easily catch fire. So we have approved cabinets that we store flammables in. Okay. And then mixing incompatible chemicals. Mixing can result in hazardous reactions. Let's say when we mix chemicals that are incompatible, okay, let's say we have oxygen and then we store it closer to, we have, we store oxidants closer to flammable. It's easily they cause explosion. So mixing can result in hazardous reactions, fire, production, and then production of toxic fumes. The level of incompatibility may depend on quantity used. So the quantity that we use, the temperature, the pressure will determine how the substance is incompatible. And then so we store incompatible chemicals separately. And then we organize experiment reactions to avoid mixing unless under control conditions. So when we have to mix chemicals that are incompatible, then they should be done under controlled conditions so that there will not be any form of um, explosion. And then we say review literature on MSDS proud. What is MSDS? Yeah, Paul.
Material safety data sheet.
Okay, so you have to review the material safety data sheet prior to the experiment. So when you are conducting an experiment, the chemical you are using, you have to read the material safety data sheet to know the characteristics of the chemical, how the hazards it comes with before using them. Do not dispose of incompatible waste in the same container. And please, do we get this part? Do not dispose incompatible waste in the same container. What does that mean? Why are we not supposed to dispose incompatible waste in the same container?
Sir,
Yes, wisdom.
uh, putting them in the same container can cause explosion or fire outbreak.
Okay, so since they are waste, they still have the chemicals in them. So putting them together will still cause a reaction. Okay. And then chemicals must always be stored in compatible groups, like we said already. And then, so look at, you see the image over here. We have an oxidizer and a flammable. What do you think will happen if we have these two stored together?
Fire.
He said,
There will be an explosion.
yes. So our second point is saying oxidizers should never be stored with flammables. Here it is, separate oxidizers from flammables. Acids should not be stored with bases, since acids react with what? Bases. Toxics should be stored by themselves, just like we store nitric acid with just by themselves. We should store toxics also by themselves. And then liquids should be stored away from solids. Why do we store liquid away from solid? Why are we storing liquid away from solid?
The liquid might be able to.
Yes, who is speaking?
Sir, I said the liquid might be able to dissolve the solid.
Okay. So the liquid can spill easily or leak into the solid. Okay. And then it might cause contamination and damage. Now, incompatible stored, this is a problem. Incompatible stored together, no secondary containers. So if we are storing incompatible closer, at least there must be a secondary container that is protecting one from the other. Acids and bases are of concern for two reasons. One, they are generally corrosive, and their reaction with each other are usually highly exothermic. When acids react with bases, they are exothermic, so we don't store them together. When we store them together, they will react with each other. That's why acid must be stored apart from each. Acid and bases must be stored apart from each other. So here you see all the chemicals over. What can you say about them?
They are labeled properly.
Yeah, so every chemical has a label on it. So we have to store all chemicals properly. We label them properly so that when you are picking this, you know this is what I'm picking. Okay. Most chemicals look alike. So if you don't, so the only thing you can use to differentiate them is the label. So if you don't look at the label, you cannot know what is inside. Okay. And then we say all secondary containers. When we pick chemicals from the manufacturing containers, we transfer them, some of them to, you see, mostly they come in large containers, and then we have to dilute or we have to transfer them into secondary containers before we use them. In that case, all those secondary containers should be properly labeled. You see, all these are secondary containers, but they are labeled. This is acetone. Yes, this is one methoxy. They are all labeled acetone danger. So we should label all secondary containers. Okay, so I think we would end here and prepare for the check service. Is that okay?
Yes, sir.
Yes, sir.
Hello, sir.
Yes. So let's yes. There's someone talking.
Last time you said you sent the slides, but still have not seen it.
I sent it to there is someone that contacted me and I sent it to the person.
Okay,
Is
sir.
it manual or something? You haven't received it still. Hello.
Hello, sir.
You haven't received the slide still.
So
No,
I
please,
think
I have
it
not
has been
received it.
sent to the page. I don't know whether it's different.
It has been sent, but I'll update it every week. So this one, I'll send this one to the page. The one I gave him was for last week's lecture only. So I'll send this one to today.
Oh, okay.
Okay, sir.
Okay.
Thank you, sir.
You're welcome. So we'll meet next week, God willing.
Okay.
Thank you, sir.
Okay.
You do well.